Hello and welcome. You're watching this video with, Allan Jude, and I want to introduce Allan Jude. He's sort of an author, developer, smart person, tweeter. It turns out he's a really interesting guy, and we're going to talk about ZFS, or ZFS for us dirty Americans, however the case may be. But we'll probably meander and talk about some other things. It's going to be largely an unstructured conversation, but I imagine that the conversation is probably going to be really interesting. So, hello and welcome. Thank you for joining me.
Hey, thank you for having me.
So, ZFS.
Yeah.
I'd say the number one question we get on our forum is, why ZFS? Why not ABC or XYZ? And until recently, I guess it wasn't included in a lot of Linux distributions, but we'll get into that a little bit more in a minute.
Yeah.
But, it's like, oh, why not BTRFS or ButterFS or, ever how you want to call it, or some other file system. But, I've sort of gone down the rabbit hole with ZFS, and it's a damn fine file system. But, why ZFS?
Yeah, so there's a couple of different reasons. The first thing is to compare something like ZFS, the next generation file system, to a classic file system, like your ext2 or 4 and UFS and NTFS and so on. Now that there's actually something to compare them to, those original file systems are called overwriting file systems. Because when you save a file, or say a newer version of a file, like a presentation I was working on and I save a newer version, what it does is overwrite the old version in place and maybe allocate an extra block on the end if the new version is bigger. With a copy on write file system, what will happen is when I save, if any block gets changed because it's different, instead of writing over top of the old block in place, I'll allocate a new block somewhere else and write the data there. And then when I'm done, I can free that block that's not used anymore. This provides two different things. First, if we create snapshots, we can keep the old version of the blocks around, and now I have the old version and the new version of the file, and any blocks that didn't change are shared between them so it doesn't take twice as much space. But the bigger difference is if the power goes out while I'm saving that data, or the application crashes or whatever, in an overwriting file system, as I'm writing over that file, if I stop halfway because the power went out or whatever, you get what's called a shorn write, because it's like it got cut off in the middle. And so now you don't have the old file because the beginning half of the old file has been overwritten. And you don't have the new file because the latter half of the new file never got written to this before the OS crashed or the power went out or whatever. What you have is a mismatch of both, which is probably not readable.
Yeah, if that's a binary format file, it's probably useless. I mean,
Yeah.
You might be able to recover a text file in that situation, but you're going to have half a new file and half an old file in a worst-case scenario.
Yeah, especially now with Microsoft Office docs or zip files full of little files, you're just hosed.
Yeah.
So the way that ZFS does it, because it wrote to new blocks, and then it updates the metadata to point to it at the end. So if the power goes out before it's completely finished, worst possible case, you have the version from before the power went out. You have the version before you started overwriting. And so you get back all your files, and maybe you lost a couple of seconds of data that didn't finish getting written. And you don't know how much of that actually got written anyway, so you're not necessarily missing it very much. Or it completes writing, and you get the new version of the file.
So not just copy on write, but ZFS or ZFS has a huge number of features that, some people would say are enterprise features, but it seems like more and more are just common sense and actually genuinely useful things. Things like built-in compression, things like, you can do subvolumes and sort of fine-tune the parameters for depending on what kind of data you're storing. It's looking to me more and more like the file system is becoming a little bit like a database. It has some of the characteristics of a database, maybe.
Mm-hmm.
But what are your thoughts on some of the more advanced features and like, quote unquote everyday use? But I'm thinking like power users here.
Right. So there's a couple of different things. One of the main things that sets ZFS apart is when they were building it for Solaris, they wanted their target user, unlike a lot of other file systems where they're written by developers, kind of for developers or whatever. The point of ZFS was to make storage administration easy, right? And so they wanted adding more storage to your server to be just as easy as adding more RAM. right? When you add more RAM to your server, you don't have to go run RAM admin and do a bunch of stuff to start using that RAM. It's just there and it just works. So the first thing they did with ZFS was pooled storage. You take all the available storage from all your disks, maybe run it through a translation layer to get, redundancy from mirrors or RAID Z or whatever transform you want to do to it. But then you just have all this space. Then you create your file systems on top of it. In the olden days, the way we did it was you partitioned your disk, and you had to decide at the time when you were creating the server that, my home partition needs this many gigs, and my operating system partition needs this many gigs, and var will be this many gigs, and I know my database will need this much space. And if you were ever wrong about that, you had to then move files to a different partition and create symlinks, or try to back up the data, resize everything, and restore it, and all kinds of terrible things. With ZFS, every one of those file systems has access to all the available free space, and you just use it as you need it. And then they let you put quotas in, so you can say, my log files can't ever take up more than 100 gigs of space because I don't want to run out of space because of log files. But you can also do the opposite of that, which is a reservation, saying my database should be guaranteed at least 200 gigs of the available free space, and don't let all the other monsters hog all that space. Make sure that my database always gets at least that much space. So that, because you don't want your database to run out of space. And the other part is just the command line interface is designed to be really easy. It's all based on simple verbs and so on. And it's just really well done. If you've not noticed, when you do, say, ZFS list or whatever, you can get very specific. You can use ZFS list with the -O flag. You specify which columns get included in the output. So you can choose only the columns you want, and you can decide what order they go in. And then with the capital H flag, it'll strip the headers off, and instead of lining the columns up nice human readable, it puts one hard tab between each one. Now, the output is shell scriptable. You don't have to run it through awk and all this other stuff. It's exactly you can read it with just a simple shell script.
Well, it makes sense, but
you've
painted yourself into a corner, though. It's sounding like this file system is for developers. No, I'm just kidding.
No, it's specifically for sysadmins, right? You can do it all with a shell script. You don't have to know awk.
That makes sense. No, yeah, right? There's when you go down the rabbit hole, there's so many things that's I never considered a file system should have this feature, but now that I have it, I don't want to give it up.
So part of it is that ZFS has grown beyond just a file system. It's also your volume manager, right? It replaces, before you would have used a RAID controller or something like LVM to combine multiple disks into one virtual disk that you could then put a file system on. Because file systems don't understand multiple disks. Well, ZFS does, because it's the volume manager, but it knows all the way down. So it does a couple of other things. So important metadata for the file system is always written 2 or 3 times. And it tries to write those writes to go to different disks that aren't beside each other. Because when they did some statistical correlation, they found that 2 disks beside each other in the array are more likely to fail together than disks that are spread apart. So they just added a little bit of code and make sure that those blocks get spread out all over the array just in case. And that way, losing a disk, and it knows about it. But one of the other big things is checksums. So every block that's written, the user data that you write, has a checksum written in the metadata. And then that metadata is checksummed, and the checksum of that metadata goes up the next block, all the way up to the root of the tree where we have the uber block, which is like the super block in a regular file system, but they're done in a circular ring, so that if an uber block's being updated and if the update goes bad because the power goes out, the drive crashes, ZFS crashes, whatever, when you reboot, it checks the checksum. Does the checksum match the data's on the disk? No, it's not all the way written. Okay, go back. Get the one before. Yep, that's the right one. Go.
Yeah.
And that way, your file system just always works. So after a crash, you just bring it up, and it's there instantly. You don't have to wait for an FSCK.
Well, that sounds really amazing, but it's so much more interesting than that, because when you're talking about a very large array, when you've got 20 or 30 hard drives, it turns out synchronizing those writes across drives, you don't really have an alternative to do it any other way, because you're not guaranteed that the drives would lose power synchronously, or it's basically an impossible problem.
Yeah. If you have external disk shelves and it's just the power supply and one of my disk shelves goes out and takes out 30 of the 400 drives in my array, I have to be able to deal with that.
Yeah.
and the other part is even when the OS sends commands down to your hard drive saying, don't tell me you're done until it's all the way on the disks and it's definitely there. Well, RAID controller firmwares have been trying to cheekily lie about that for years to make them have better performance numbers.
Yep.
They're like, oh, it's in our battery-backed cache now, it'll be fine, unless the battery dies.
Yeah. Yep. And that's not even a perfect solution either, because you're unless you have a really complicated setup with like multiple RAID controllers connected to the disk shelf, but the software on that is buggy. Every time I've experienced a failure from that in the enterprise, it is almost, if it's not, controller failures happen, and the redundant controller failures are more common than you think in the enterprise, especially when you're dealing with a lot of spindles, and there's really not an elegant way to handle it, quote unquote, in hardware.
Right, and getting a firmware update for that card can be really difficult, whereas this is open source software you can actually dig your hands into if you have to. You don't want to, but you can if you have to.
Now, one of the common questions that comes up on the forum and with users that are sort of new to ZFS is, it's sort of back to your point about it's really easy to add storage, but you can add more storage to a pool, but every puzzle piece that you add to the pool, for lack of the proper term, has to have enough redundancy in and of itself, because if you lose one of the components, you would lose the whole pool.
Yes. So the way ZFS was designed is you have these virtual devices, which is a bunch of disks combined with some kind of transformation to make it into the backing store, and the transformation is responsible for providing the redundancy. So if it's sets of mirrors, then the mirroring is designed to provide the redundancy. Or if it's RAID Z 1, 2, or 3, or that provides the redundancy at 1, 2, or 3 disks of concurrent failure. But yes, if you have a very nice RAID Z array and then you add a singular disk as a second VDEV, and that one disk goes away, now fraction of all your writes are gone, and so all your files have holes in them, and your pool is useless.
But the interesting thing is that the writes will be balanced as you add sort of not necessarily symmetrical VDEVs to the pool.
Yes, although there's actually been some changes to that. So originally, the throttling for writes was specifically designed to each VDEV would arrive at about 95% full at the same time. So a more empty VDEV that was added would get a larger portion of the writes. With the new write throttle and allocation throttle that were introduced in the last couple of months, the change is that you take up the work you want to do, you divide it into pieces, and you give each VDEV a piece. And whichever VDEV is done first gets the next piece.
Oh, neat.
And you just keep allocating pieces to keep the work queue of each drive full, but ZFS doesn't decide ahead of time who does more work. So the fastest disk gets more work. And because of the way ZFS and the fragmentation goes, the fuller a disk gets, the slower it gets.
So it sort of automatically works its way out.
But the point is that, if you stick in a mostly empty VDEV, it's not going to actually slow your pool down by taking more writes than it can handle anymore. It will take more because it's the fastest device, but eventually things will balance out.
Well, now, you have a lot of experience with very large and probably, I imagine, long-lived pools. With the copy on write mechanism, as you keep snapshots and then expire snapshots and deal with large files and deal with files that are being shuttled around, does fragmentation become a problem? And if so, in what workloads?
Yeah, so my workload's mostly not, because I'm dealing with very large files. So mine are almost all video files. So they're 300 megs to 8 gigs, and they're written once and never modified. And they're usually written all at once. And so they don't end up very fragmented on the disk, and they never get modified, so they don't get holes punched in them. So my case is like super optimal case. Whereas a database is not such an optimal case.
So if you are in a situation where you're running a database, are there different things that you can do to the pool to sort of tune the performance, or the data set, I guess I should say? Is that the right?
Data set's the right one. So with a database, the most important thing is to make the record size of the data set match what the database is going to do. So like on MySQL, InnoDB is 16K. If you leave the default ZFS, which is 128K records, it means MySQL writes a bunch of data, so ZFS breaks it up into 128K chunks and writes it to the disk, and then somebody does an update or something, and InnoDB wants to update 16K. Well, ZFS is going to have to read the whole 128K, modify some 16K in the middle of it, and then write the whole 128K again. So now you've created a read every time you want to write, which is going to hurt performance, and then you're writing more data than you actually wanted to.
Yeah.
And so that's how you get this write amplification and the read, modify, write cycle that you really don't want. Whereas if ZFS is set for 16K records, then it'll match one for one, and it won't have to do any reading.
And that's when you're that person and you're thinking through these issues. That's you sort of do that, and you start to realize that it's like really understanding how the file system works. Whether you're an application developer or a database admin or a system administrator or whatever, really will help you tremendously in the performance of your application.
Yeah. The other thing that can help a lot is tools in the operating system that you actually observe what's happening. So one of the big things ZFS has is very good integration with dtrace, which is this dynamic tracing framework from Solaris and FreeBSD. The idea is that you can it's a safe way in order to view what's happening in the operating system at a very deep level, like when individual functions are being called, or there are static probes built into ZFS as well, and get that data, but in a way that you can do it while the system's working without having a performance penalty. So what dtrace does is basically dynamically patch the running system to call a little bit of code at the start or end of a function. And so that means that when dtrace isn't running, there's no performance penalty. And then you can turn it on without having to stop the program. Whereas normal debugging in an application, oftentimes you have to recompile the application to enable it because of the performance penalty it has, or restart the server program with a special switch to make it print out the extra information. But if the problem only crops up when the server's been running for over a month, then restarting it to enable the debugging with reduced performance and then have to wait a month for it to happen again that's not really an option.
We could do another video on dtrace, because that's probably coming, actually, because it's a really handy tool for those kinds of situations.
Yes, at a number of the BSD conferences that happen around the world, there's a tutorial taught, dtrace for practitioners, and it's for sysadmins and programmers to get a basic start with dtrace. It's very helpful. I took it when I was in Tokyo. I was actually helping somebody debug a ZFS performance problem today. So they have a FreeBSD VM running inside KVM on top of a Linux machine. And they noticed when they ran FIO to do performance benchmarks that the performance they were getting was really bad. So they had allocated this VM to have 256 megabytes a second of transfer and up to 8,000 IOPS. And when they ran FIO, they were getting nowhere near that. And they were like, why? When I run UFS or Linux, it works fine. Well, it turns out they had the 128K record size, and they were telling FIO to do random overwrites at 4K. So they have to do these reads. And they'd done the right thing and disabled the caching in ZFS to run the benchmark, because otherwise you can get impossible numbers like, I can read at 30 gigabytes a second off this hard drive.
Yeah, because it was from RAM
or
whatever.
From RAM, right?
Yeah.
But because that was off, it meant every time they were writing 4K, it's read 128K, modify the first 4K of it, write it back, read it back the whole 128K again, modify the second 4K, write it out.
Oops.
So once we created a 4K dataset and solved that problem, then they had the problem of trim. Because the device their KVM is exposing claims to be an SSD and support trim, ZFS is trimming blocks after it's used them. So they start writing, it works good for a couple of minutes, and then ZFS is like, okay, I'm done with some of these blocks, I'm going to delete them now. But their backing storage can only handle so many deletes a second, right? Because on an SSD, trim is actually kind of an expensive operation.
Yeah.
And they would end up causing so many trims to happen that it was choking out how many reads they could do.
Yeah. Yeah, the trims are supposed to happen only when all of the other queues are empty. Yeah.
Well, there's also a limit on how many trims you can have queued up as well, though. There's 10,000 trim operations that need to happen. Eventually, you have to flush them out, right? You can't just keep them all around forever.
It's fine. No, that sounds terrible, yeah.
Yeah, so there was some interesting things there. But I think one of the other big features that I really love of ZFS is the replication. For a bunch of the stuff we do, we have to replicate data from our master servers in Toronto to servers in like Germany and Australia and all over the world. If we tried to use rsync for that, every time we did the rsync, it would have to walk through all of the files, check the dates on them, and if the dates are different, then it has to read the file and checksum each chunk and then decide if that chunk's different than the other one. So you end up doing reads on both sides and then comparing the numbers and all this stuff. And then in the very end, you find out nothing has changed.
That sounds like a nightmare of I/O. That's just not good.
Yeah. Like there were a few FreeBSD servers in the FreeBSD, like the projects cluster, where we have home directories for all the users. Every developer there's been and the home directories are original, going back like 30 years. And at the time, they were stored on a NetApp instead of ZFS. And so they're doing an rsync trying to copy them from California to New York. But the process took over 24 hours, even when there was only a couple of kilobytes of differences, because they had to read every file and compare them. ZFS doesn't have that problem because of the way it works. So while rsync has to walk every directory, look at every file, check the stats on it, and then possibly read through the file, what ZFS does is when you create a snapshot or a bookmark, it basically keeps track of the time when that was taken. And so when you do incremental replication in ZFS, where you say, all right, I've already replicated up to this point, just give me everything that's changed between there and this other point, it just looks at the disk and say, give me every block that's changed that has a birth time of this or higher. And so it can just start saturating your network right away.
Yeah.
So you can just start sending 10 gigabits a second to the network right away without having to check any metadata at all. It doesn't know that they're files or care that they're lots of little files or one big file like rsync does. Right? With a lot of little files, rsync will be even slower than one big file. ZFS doesn't care because it's just a stream of bits on the disk.
And that kind of thing also comes in handy for things like deduplication, where you can keep sort of the checksum of the block and it doesn't care. And it's like, oh, I've already seen this block before. It's in my database. It's just on the remote end, it's like just make block 37 that you already have.
Right. Although deduplication is I would avoid that feature if you can for now.
It is a RAM hog.
Yes, like really bad. And the bigger problem is it'll work fine until the dedupe table gets bigger than you can fit in RAM, and then it just falls over. In the next year or two, we'll see a feature called metadata classes that allow you to say the dedupe table specifically lives on this SSD, which is dedicated to just that.
Cool. That would be awesome.
And that'll solve the problem a lot, especially if that instead of an SSD, that's say an NVMe that can do 4 gigabytes a second, and 500,000 IOPS, but also a separate feature that will basically say stop deduping when the SSD gets full. So that instead of falling over again, you can just say, all right, I've deduped all the things I can dedupe. Let's avoid that. Although Matt Ahrens also proposed an idea. Matt Ahrens is one of the original co-creators of ZFS with Jeff Bonwick at Sun. But he proposed an idea of, so you have the dedupe table, which is basically the hash and how many times it's been appeared in the file system. When the dedupe table is full and we go to add another entry, right now, what it does is expand the table and won't fit in RAM now, and you'll get the swapping going back and forth and your performance will be terrible. The new idea is that when it reaches some limit, it will find some file that only has one reference in it and remove it from the table and insert this new entry. The idea being that now when we go to delete a file, if we check for its checksum and it's not in the dedupe table, we know that was the only copy and we can throw it away. Whereas if we delete a file and check in the dedupe table and see there's 4 other files using that shared block, then we know not to throw it away.
Cool.
But this will allow files that have up till now never managed to dedupe, and the dedupe table is now full, we assume that file is just unique and is never going to get deduped. Kick it out of the list to make room for a new file that maybe will get deduped, which will allow us to have dedupe with some limit set to it, or you only give it this much RAM, and dedupe as best you can, and if it's not perfect, it's not perfect.
Yeah, and so dedupe, in a nutshell, then dedupe has a lot of. It's probably not for the casual user, not for somebody that doesn't know what they're doing. Yeah,
and especially if your dedupe ratio is going to be less than 4 to 1, the transparent compression will probably do better for you anyway.
Yeah, well,
With almost no cost.
I'm glad you mentioned compression for two reasons. One, it is a little somewhat unusual to have compression built into a file system. You would think that there would be a penalty associated with it, but with ZFS, really not so much, as far as I can tell. It depends on the compression, I guess.
Yes. So the default compression algorithm originally was LZJB, which was written by Jeff Bonwick. That's where the JB part comes from. It was relatively performant, but the compression ratios were not very good. It was like 1.5 to 1 or something like that. But a number of years ago, that was replaced as the default with LZ4, which was written by Jan Colette. It gives you a compression ratio of about 2 to 1 on most files that are actually compressible, and obviously 1 to 1 on files that aren't compressible. But it does it at really high speeds. Like compression is about a gigabyte per second per core on any modern-ish machine, laptop or desktop or server. And on a server, if you have 32 cores, then that's a lot of gigabytes per second of compression. And more importantly, the decompression is usually 2x or more better than that. So you can get like 2 gigs a second of decompression. And so super fast. It also supports gzip, which gives you better like 3 to 1 compression rates. But the problem with gzip is that your compression speed is only about 50 or so gigabytes per second per core, or sorry, megabytes per second per core. And now if you're doing that, on a laptop with say 4 cores, that can end up being a lot slower than your disk. And you'll notice that, and you'll notice all your CPU time being spent in gzip. But LZ4 gives you almost as much compression, 2 to 1 instead of 3 to 1, but at such a low CPU cost that it's actually quite reasonable. The other thing it has is what's called early abort. The buffer ZFS provides to the compression algorithm is specifically like 87.5% of the size of the input block. And if it doesn't fit in that block, it gives up on compressing it.
Oh, cool. So if it can't compress it, it just doesn't even bother trying.
If you're not getting enough compression for it to be worth it, store it uncompressed so you don't waste time decompressing it when you go to read it.
Nice.
There's actually another feature proposed by Nexenta that I expect to come in the next year or so called smart compression, which will also look at on a per file basis, be like, every other block we've written to this file turned out not to be compressible. So let's just skip trying to compress it for that file. But every so often it'll try one again to see if it's changed. Because, if you say you got the backing disk for a VM, the first bit you write to it maybe isn't compressible. And then later the stuff you write is, and it'll adapt. But most times, if it turns out this is a giant tar.gz file, we know it's not compressible. Let's stop wasting time trying to compress it and adapt, basically.
Now, is that the new compression that you were telling me about the other day?
Other interesting thing is there's a new compression algorithm that Facebook had Jan Colette create. So the person who created LZ4, which gave us this really, really high speed but moderate compression algorithm, has created a new one called Z Standard. What it does is provide both the same compression as gzip, sometimes a little bit better, so 3 to 1 compression, but at high speed, like 400+ megabytes per second per core, and decompression at 800 to 1 gig per second of decompression. So now we have an algorithm that gives us the compression of gzip, but does it fast enough that even on a low number of core laptop or something, is going to be much faster than an NVMe that we're going to have, or the 4 or 6 spinning disks we might have in our home file server, or NAS. So now, we can get even better compression, still fast enough that it's not going to be slower than our disks. Now, it will use more CPU, but most times your NAS has a decent CPU and nothing else to do with it. Right?
So what I'm starting to notice a pattern in our conversations when we're talking about the architecture and this is really just like the kiddie pool version of the architecture. I mean, we're staying really high level for the audience to understand, but the more I hear, the more it sounds like ZFS is really ahead of the curve on just about everything, because hardware is catching up, and interface speeds are catching up, and ZFS and a laptop, something that was developed by Sun Microsystems originally and had hundreds of programmers working on it, but is now on a laptop.
One of the big things to think about with compression is, especially with, say, databases where it's full of text that's very compressible, most people would have thought, well, compressing it will be slower because we're going to spend this time compressing it. But especially with LZ4, where you're compressing so fast, you can actually end up getting better speeds by turning compression on. It seems a little counterintuitive, but if you think about it, if you're writing 200 megabytes of data and it compresses 2 to 1, so then the compressed version only takes 100 megabytes of disk space. Now when you write that out to your disk, you only had to write 100 megabytes to the disk, which maybe, say, a regular spinning hard drive, say, can do 100 megabytes a second. Now it took 1 second instead of 2 seconds to write that data to the disk. You've basically effectively written 200 megabytes per second to a disk that can only handle 100 megabytes per second. Imagine doing that to an NVMe that can do 4 gigs a second. Now it can do 8 gigs a second, as long as your content is compressible.
That sounds amazing. I need that in my computer.
And so one of the interesting new features that they came up with is the compressed ARC. So the ARC is the adaptive replacement cache. It's the cache ZFS uses. So most file systems have what's called an LRU cache. So basically you have a list of the most recently used things, and when you use a new thing, it goes in at the top of the list. And when the list is full, in order to make room, you delete the least recently used item, so the thing at the bottom of the list. And every time something gets used, it moves back to the top of the list. So the problem with that type of setup is if you do something like, say, take a backup where you read every single file on the disk, you're going to churn through that list and throw everything away. Right? You have how many terabytes of data and only 10 gigs of cache space, and so you're just going to churn it a bunch of times and throw it all away. So what the ARC actually has 4 lists instead of 1. It has the most frequently used files and the most recently used files. So files you use a lot are kept in one list, and files that you've used recently are kept in another list. So when you do a backup, that will trash the most recently used list, but it won't affect the most frequently used list. So files you've been using the whole time, like, say, your database, aren't going to get thrown out of the cache. And then it has ghost lists of each of those two, where it keeps the list of things that were in the cache but were removed because they weren't being used often enough. And it uses that as a ban list to, when something comes up and maybe should go on the cache, it's like, well, you've already had your turn and you didn't end up being very useful. Let's give someone else a chance to be in the cache, and maybe they will. So it does that. Anyway, so the new feature with that is if the data happened to be compressed on the disk, before what was happen is we'd read it off the disk, decompress it, and then store it in the cache. The new feature, compressed ARC, says, well, why don't we leave it compressed? Now our cache can fit twice as much stuff because all the compressed blocks stay compressed. It's like, well, there's a cost, obviously. You have to decompress it every time you read it out of the cache. Yeah, but if I can decompress it at 1.8 gigabytes per second per core, that's not really that big of a concern.
Didn't RAM compression companies in the 90s build the .com bubble, though? I mean...
Well, so the difference here is that all the RAM compression techniques, what they do is wait until the system's running out of RAM and then retroactively try to compress things. Well, the problem there is you need to allocate some RAM in order to do that. And if you're in a situation where you're running out of RAM, that's probably not what you want to do. What this one is doing is say, let's delay the work of decompressing this until it's actually used a second time. Now, there is a new little cache, I think it's only about 100 megabytes by default, of things we've decompressed like this second. So that if you're reading a file many times a second, it'll actually keep the decompressed version around. But in general, because the decompression is so fast, you don't need it.
That sounds like that was added to deal with an edge case that somebody encountered.
Yeah, well, specifically databases with indexes, where the index is used constantly.
Yeah.
But yeah, with the new compressed ARC, on my machines, I'm seeing like 1.75 to 1 memory compression. So all of a sudden, I can fit 60 gigs of ARC in a machine that only had 32 gigs of RAM. It's like, nice. Well, I'm winning. So yeah, there's that. And then the other one they found, I guess they just didn't think of this when they originally designed the replication system, but Part of the point of the replication system is that it turns the file system into a serialized stream. So it gets rid of anything specific and allows you to create compatibility. So you can, if you do the ZFS replication, by default, it dumbs everything down to the lowest common denominator. It means you can send it to a pool of a different version, including an older version. Now, there are some flags you can set to enable newer features in order to keep those as they go across. But by default, what it did before was uncompress any blocks and send them over the network uncompressed, which a lot of people didn't like, right? So you'd end up running ZFS send, piping it into like gzip or pigzip or something that's multi-core gzip, and then over the network, and then ungzip it, and then pipe it into ZFS, which would then be like, oh, you want that compressed, right? Compress it with LZ4 or whatever, and then write it to the disk. So now that they have the compressed arc feature, it means the data as it's being read isn't being uncompressed. So it can actually send the compressed version over the network. So with that feature, you'll be able to do compression or replication and leave the compression on all the way across. So
that sounds a lot more efficient.
Yeah. So that'll have an advantage as well. And it also does support, when you receive it on the receiving side, it can decompress it and recompress it if you want to use a different algorithm. So
that could be handy.
Yeah.
For like an archive, you would maybe be okay with gzip on the replica.
Exactly. One of the examples in, I think, the first ZFS book that Michael Lucas and I wrote was he worked for a company that was contracted by AT&T to store the records of phone calls. So these basically giant text files full of the metadata of phone calls, like who called, when, for billing purposes. Well, in a 10-year-old version of that record, it's never going to be modified and rarely ever read, but you have to keep it around. So why not gzip -9 it, right?
Yeah. That makes sense.
On the recent records, maybe you want to keep them in a compression where you can read them quickly. But on other ones, you're like, yeah, that's archival. Just compress the hell out of it.
Even with all the insanely awesome features, I want to be clear that this is not any kind of thing that makes ZFS any more inaccessible for everyday use. Like, the more that I've used it, especially on modern systems, I mean, honestly, these kinds of things are becoming, to me anyway, everyday features. And not because it has the features doesn't, and it is more complicated than a normal file system, but that's no reason to be intimidated by it and no reason not to use it on your everyday system.
Yes, in particular, one of the features that Solaris invented that FreeBSD has adopted wholeheartedly is boot environments. So this is the idea that you have your OS as one of these file systems, and before you install some upgrades or update your packages or install a new version of GNOME, you take this snapshot and we actually clone that and make a new file system out of it that takes up no extra space, but it's a writable copy. So any changes you write do take up space. So we keep a clone of how your system was before the update. Then we do the update. You try it. So you finish the update, you reboot and you try it. And now, the new version of X has this bug, or GNOME backfired and didn't install, or it's just all gone to hell and I can't use it. Well, reboot again, and in the boot menu, it could be in Grub or in FreeBSD's native bootloader, and you go into the menu and you say, I want the system how it was, before I installed GNOME. And it switches the root file system to that one and boots up. But the important thing is your home directory, your mail spool, your database, any other file systems you created weren't reversed. Only the operating system. So, the new emails you've downloaded in Thunderbird in the meantime while trying to do this X upgrade or whatever are still there, right? Or you revert the OS on the server after an upgrade that didn't go well. You don't want to back up the database and lose all those new orders. Those you leave separate.
Yeah, that's the value of having the different data sets for everything.
Yeah.
So
that's one thing I see that people don't necessarily do enough of, especially when they're using it as NAS or something, is you want to try to break up your files by use cases and so on, but also, if someday you're going to need to replicate this somewhere or move it, or, at one point I had my NAS was built with 4 drives and I wanted to switch to 6 drives, but I wanted to rebuild the array differently. So having my files split up into like 400 or 500 gig chunks meant that I could put half of them on one temporary disk and half of them on another temporary disk while I rebuilt the array. if I put them all in just one giant file system that was 3 gigabytes or 4 gigabytes, or sorry, terabytes, it wouldn't have fit on any one new disk. And I would have not had a way to do this. I would have to use rsync, and it would have been forever.
Yeah, that's kind of a mess, because we're back to the whole reading everything and having to compare everything, and then it's IOP central, and that's bad.
Yeah, and so really, what my advice there is to try to create data sets for every bit of data you might want to treat differently, not just necessarily ZFS settings, because that's the main use of creating the data sets, but just where you might have different uses for, or you might want different permissions on, or just, some of my archives are broken up by genre, just so that there's some logical separation to categorize stuff.
That might be a little over the top. That's probably like music genre. It's like, oh, we've got the 60s in this data set.
Music files are small, but there are other types of files you might have on your NAS that are bigger.
Makes sense.
So then, get back to your original question of why ZFS. The other comparison you have are newer next-generation file systems like ButterFS and so on. The main difference is that ZFS has been in production for 15-ish years now, and it's actually been used by people. And the biggest, I think, thing there is Sun had a QA team that did a really good job and set the culture for everything. But the main one is that the actual engineering that went into the design and building of ZFS, there are over 100 engineer years of effort that have gone into ZFS. And that's made it a lot more polished than a lot of the newer competitors. And while they might someday get there, how are they ever going to catch up to 100 engineer years? It's like, even if you had 300 people working, 8 hours a day for 3 years, they might eventually generate 100 engineer years worth of effort. But, ButterFS doesn't have 300 people working 8 hours a day for a year to catch up. And, there are still people working on ZFS. That's one of the big things is when Oracle bought Sun, they closed sourced that ZFS. But we forked the last open source version, and we have OpenZFS, and there's actually a lot more work happening there than in the proprietary one. And so I would say there's probably at least as much effort going into new features in OpenZFS than there are in building ButterFS. And so ButterFS is always going to be 100 engineer years behind.
Well, not just the level of engineering that's going into it. I mean, it's obvious that tons of new features and new functionality is going into ZFS or ZFS, but also the hardware that you run it on is catching up to where that, the argument about, LZ4 compression is too much overhead it's a non-issue anymore, because the hardware is there. The hardware is insanely fast these days compared with, where the bottlenecks are.
The new Intel Optane things are 4 gigabytes per second read and write and 500,000 IOPS. That's one of the things, when they set out to build ZFS, they're like, we're going to over-engineer the hell out of this because we want this to be the last file system you ever have to upgrade, right? Like, if you had to upgrade from ext2 to 3 to 4, and then there's going to have to be a bigger one someday when the hard drives get bigger. Currently, to reach the limit of what ZFS can do as far as storage size, with current technology, the power required to power the hard drives, like the electricity required to power all the hard drives that were required to reach that amount of data, which is like 128 zettabytes or whatever, would boil all the water in all the oceans on the planet.
Well, I think that size file system would probably be sufficiently large then.
Yeah.
We're going to have to, that's storing what, like 2-3 bits per atom to get
Something
it
like
into
that.
a reasonable size?
And you can have like 128 billion data sets.
And by the time other file systems like ButterFS add the same level of features, it's going to have the same level of...
It's not just features, it's reliability.
Well, yeah, that's true.
That's the bigger one, is that, ZFS, ever since it went public, has always been a reliable file system. There have been little bugs and stuff, and they get addressed, but it's not been anything embarrassing.
You can only be talking about the RAID 5 thing with ButterFS, right?
That one mostly caught me out because of a specific anecdote, though. So it turns out what somebody did was create, the guy who found this bug, he created a new ButterFS pool backed by files, and then he like deleted or zeroed out one of the files, and then had Btrfs try to recover it. And what he found was, instead of recovering his original data, it just scribbled gibberish. And I was like, that sounds very familiar. And I looked back to FreeBSD has what's called the FreeBSD handbook, which is basically a giant thing that used to be printed but isn't anymore because it's a waste of paper, of basically a manual for the operating system. It's got like 38 chapters, and it walks through all the different concepts in it, including like configuring your IP address to, a whole chapter on ZFS, or, how to use a serial terminal and how to print and all the different things you could do. When trying to describe to people how ZFS works, one of the experiments we had them do was create a new Z pool backed by a bunch of files and then delete one of the files and then watch ZFS recover it. So if you've gone through the manual for ZFS on FreeBSD, you've done the exact experiment that the Btrfs failed. It's like, so every new ZFS user does this exact experiment to learn how ZFS works, and one person tried it on Btrfs and found out it never worked.
Oops.
Oops.
Oh, well, it's been amazing. Is there anything else that you would like to plug, or any other work that you have that's, hopefully this is not the last time that we do this. Hopefully the audience is like, oh my God, let's go buy the book, because there's actually 2 books. And
yes, you can go to zfsbook.com to find those 2.
Yep. And there will be a link in the description.
There you go. Thank you. I also do a weekly podcast about what's happening in the BSD family of operating systems. That's bsdnow.tv. That comes out every Thursday. It's recorded live every Wednesday.
That will also be in the description?
Yes. And I think you might be on it next week, right?
Oh, yeah, that's right. Yeah. I don't know what... it's internet bozo. I don't really have a lot to talk about. It's like, I'm working on this amazing file system or this new compression. No.
Well,
it's
I'd like to hear how Linux people get along with ZFS too.
Yeah, I'm running quite a. There's probably about a dozen good-sized ZFS or ZFS pools that I support, and our the video storage server that we use is made from garbage, but it's 4 disk shelves, four 24 disk shelves. It's an old NetApp that's been sort of recycled. Yep. And so it's about 170-ish terabytes of storage. Well, there's actually, I've got a mirrored pool and then just bulk video storage. In the mirrored pool, it's 2 4-drive mirrors for virtual machines, because I found that to be a lot faster than RAID Z.
Yes, pools or mirrors are always your best bet for IOPS, because with RAID Z, all the disks, basically you get the performance of 1 because they're writing in lockstep. Yeah. Whereas if
there's a handy table in the book.
Yes, there's a handy table in the book. Although that book, we talked a little bit about NVMEs as well, but there's a big difference between using a bunch of spinning disks that can do about 250 IOPS each, and maybe 100 megabytes a second of linear writes, versus an NVMe that can do 4 gigs a second and 500,000 IOPS a second.
Yeah, I am using an NVMe for a separate log device. I have it's a 400 gig Intel NVMe, which is the smallest one that I could get, but I'm only using about 100 gig chunk of it. And
for your S-Log, I'm guessing if you look, you'd never use more than 8 gigs of it.
Well, I tuned the thing so that it's 30 seconds. I think it'll float for 30 seconds instead of 5 now, because all I'm ever doing is copying huge video files to it, so I don't care.
Yep. I can show you a couple. I think in the second book there's a little bit of tuning I did when I had to purposely duplicate a set of data. So I had about 25 or 13 terabytes of data, and I needed to ZFS send it back to the same pool for a different customer. But exactly the same 13 terabytes of data. So replicating 13 terabytes over localhost and trying to make it as fast as possible, which basically partly consisted of, instead of flushing every 5 seconds, only flush once every 30 seconds, or once you've accumulated 24 gigs of data in RAM, and then you want to flush that.
Yeah, that's pretty much what I actually had a lot of fun farting around, even with just the cabling and playing with different RAID Z configurations, figuring out, like, do I make it so that I can lose an entire shelf, or do I split up the writes across shelves, or what do I do? That was a lot of fun playing with that and just sort of experimenting to see what worked well for the workload. But most of the workload, we do live editing, so our video files do change a little bit on the storage. So we do have a little bit of a fragmentation that may crop up someday, but it's fine.
One of the things we recommend in the book is if, for example, you're using BitTorrent, which I think is also 16K chunks, you want one data set for where you download it when you're writing all over the place. And then most torrent clients support moving a file into a different directory when it's finished. Well, if you do that to a different data set, it's going to copy the file linearly, so when you write it into your long-term storage, it's defragmented.
Yep. So what you're saying is if you ever fear fragmentation, just make a new data set and copy all your stuff to the new data set.
Yeah. But, at the pool level, that won't necessarily help, but for file level fragmentation, it will.
Okay.
So it won't defragment your free space, but it will defragment the file as long as there's some free space to defragment into.
Oh, yeah,
if you need to defragment the free space because your pool is totally crazy, then you basically need to send it off and send it onto new disks.
add yet more storage. I think that could be arranged.
Exactly. Well, it's shelves, right? You just connect more shelves. It's fine.
Well, it has been an awesome conversation. Thank you. Thank you very much. And I will see you in a week. And hopefully I'll remember to update the description with the thing to the one that I was on. And maybe that will be good. So,
cool. Thank you.